Today, we will discuss section 1.4, which is composition of functions. Goals. Today, our goal is to do the following. 1. Evaluate a function composition in the given forms. A. Table. B. Graph. C. Equation/formula. 2. Compute a composition of functions and analyze the resulting composition. 3. Given a function composition, determine the functions contained in the composition. What is function composition? Composition of functions. When the output of one function is used as the input of another, we call the entire operation a composition of functions. We write f parenthesis g of x parenthesis and read this as f of g of x, or f composed with g at x. An alternate notation for composition uses the composition operator open circle. F open circle g of x is read f of g of x, or f composed with g at x, just like f parenthesis g of x parenthesis. You could view this as outer parenthesis inner of x parenthesis. A function within a function. Function composition examples. A rough estimate for the gas mileage of a car can be computed as a function of joules, unit of measurement to compute work, m of j. To compute the amount of work an engine is putting forth, the weight of the passengers as a function of how many people, n, are in the car can be computed by the function j of n. In context, what would the value m of j of 5 compute? If we think of this as outer of inner of x equals m of j of 5, we observe that j of 5 is equal to the weight of 5 passengers. So what we are doing is m of the weight of 5 passengers. This is resulting in the gas mileage of the car given that there are 5 passengers. Evaluating function composition with tables. Here we have two tables, a blue table and an orange table. The blue table corresponds with the function f of t. The orange table corresponds with the function g of t. Each table has two columns, the t column and the f of t column, or the g of t column, respectively. For the f of t table, we have the t values -1, 0, 1, 2, and 3, and the f of t values 2, 4, 5, 6, and 8. In the g of t table, we have for t, -1, 0, 1, 2, and 3, and for g of t, we have 5, 6, 7, 0, and 2. Given the tables of the functions f of t and g of t, compute f of g of 2. Procedure. 1. Compute the inner value. Observe that our inner value is g of 2. So if we observe the t value of 2 in the g of t table, we see that the corresponding y value is 0. We denote this with an arrow going from 2 to 0 in the g of t table. Thus, we have that g of 2 is equal to 0. For the second step of our procedure, we plug 1, the value we got from the first step of the procedure, into the outer function. In this case, our outer function is f. So what we are computing is f of g of 2. Observe that we know that g of 2 is equal to 0, so what we are finding is f of 0. Thus, we go to 0 on the f of t table, and we draw an arrow to its corresponding y value, which is 4. Thus, we have that f of g of 2 is equal to 4. Evaluating function composition from graphs. Here, we have an xy grid with the range of the x values going from -2 to 4, and on the y-axis, the range of values going from -1 to 4. We have two functions represented, one in red and one in blue. The one in blue is a cubic function with its saddle at 1, 3, the coordinate pair. And the second function in red is the absolute value function with its vertex at the coordinate pair 3, -1. Given the graphs of these functions, f of t and g of t, we are asked to compute g of f of 3. Procedure. 1. Compute the inner value. Observe that our inner value is f of 3. So for our red function, which is f, we go to the x value of 3, and we find that its y value is -1. We've circled this coordinate pair 3, -1 on the graph. So we have that the y value is -1. The second step of our procedure is to plug the result from 1 into our outer function. In this case, our outer function is g, which is the blue line. So now we're going to compute g of f of 3. We know that f of 3 is -1. So now we are going to find the y value for the corresponding x value on the graph g, which is the blue line, being -1 as the x value. So we draw a vertical line at x equals 1, and we see that we intersect the blue line with a y value of 1. Thus, we have that g of f of 3 is 1. Evaluating function composition in equations. Given that p of k is equal to 5 minus k squared and q of k is 2k plus 3, compute q of p of -2. Procedure. 1. Compute the inner value. For the inner value, we're going to compute p of -2, which means everywhere we see a k in the function p, we're going to put -2 in its place. Thus, we have 5 minus, in parentheses, -2 squared. It's important to observe that -2 squared is +4. Thus, we have 5 minus 4, which is 1. Second step of our procedure. Plug the result from 1 into the outer function. Now we are finding what q of 1 is. So everywhere we see a k in the function q of k, we place 1 in its stead. So we have 2 times 1 plus 3, which is 5. Thus, q of p of -2 is equal to 5. Computing function compositions. Example 1. Given that f of x is 2 minus 3x and h of x is 2x squared minus x minus 11, compute, part A, f of h of x. For f of h of x, we're going to start by inputting the equation for h of x, which is 2x squared minus x minus 11, into our f function. So we have f of 2x squared minus x minus 11. So everywhere we see an x in our function f of x, we're going to place 2x squared minus x minus 11 in its stead. Thus, we have 2 minus 3, in parentheses, 2x squared minus x minus 11. After utilizing the distributive property, we have 2 minus 6x squared plus 3x plus 33, and after we collect our like terms, we have -6x squared plus 3x plus 35. The orientation of these terms is exclusively aesthetic. As you will see later on in the course, the equation solving component of these types of equations are really not changed based on the ordering of the terms. Part B, h of f of x. For h of f of x, everywhere we see an x in the function h, we are going to put the equation 2 minus 3x in its stead. So we have h of 2 minus 3x, which begins with the process 2 times the quantity 2 minus 3x squared minus the quantity 2 minus 3x minus 11. This is going to require some algebraic fancy footwork, but we'll do our best to demonstrate this. Off to the side, I have that 2 minus 3x squared is the quantity 2 minus 3x multiplied by the quantity 2 minus 3x. Thus, I have to use binomial multiplication techniques to expand this operation. So when I utilize the multiplication of the first terms, I have 2 times 2 is 4, The outer terms, 2 times negative 3x, I get minus 6x. Negative 3x times 2 is negative 6x, plus 9x squared, which is the result of negative 3x times negative 3x. After I collect and reorder the terms, I have 4 minus 12x plus 9x squared. Now observe that that is still being multiplied by 2 as the first term in my composition. So I have 2 times the quantity, 4 minus 12x plus 9x squared, minus the quantity, 2 minus 3x plus minus 11. After utilizing the distributive property, I have 8 minus 24x plus 18x squared, minus 2 plus 3x minus 11. Observe that the minus 2 plus 3x came from distribution of the negative. Next, after I collect and reorient my terms, I have 18x squared minus 21x minus 5. Example 2, computing function compositions. Let f of x equal x squared and g of x equal 1 over x minus 2x. Find f of g of x and g of f of x. First, we find f of g of x. F of g of x is equal to the quantity g of x squared. Since g of x is 1 over x minus 2x, for f of g of x, I have the quantity 1 over x minus 2x squared. Many students will feel compelled to continue to expand this operation or expand this resulting function. That leads to no additional information about the function, so I would consider this to be superfluous. This is not necessary. This is a correct answer as written on the slide. Next, we will compute g of f of x. This would be equal to 1 over f of x minus 2 times f of x. Our equation for f of x is x squared, so for g of f of x, we have 1 minus x squared, 1 over x squared minus 2x squared. Let me repeat that. G of f of x is equal to 1 over x squared minus 2 times x squared. Computing function compositions, example 3. A city manager determines that the tax revenue, R, in millions of dollars collected on a population of p,000 people is given by the formula R of p equals 0.03p plus the square root of p. And that city's population, in thousands, is predicted to follow the formula P of t is equal to 60 plus 2t plus 0.3t squared, where t is measured in years after 2010. Find a formula for tax revenue as a function of the year. To solve this particular question, we are really being asked to compute the function R of P of t. So for R of P of t, we have the function 0.03 times P of t plus the square root of P of t. Thus, we have that R of P of t is equal to 0.03 times the quantity, 60 plus 2t plus 0.3t squared, plus the square root of 60 plus 2t plus 0.3t squared. We will utilize the distributive property and reorient the terms reorient the first 3 terms of this. Thus, we have 0.009t squared plus 0.06t plus 1.8 plus the square root of 60 plus 2t plus 0.3t squared is the function R of P of t. Observe that reorienting the terms under the square root yields no algebraic utility, so we don't need to do that. Computing function compositions, example 4. Write f of x equals 3 plus the square root of 5 minus x squared as the composition of 2 functions. We have a lot of agency as to how we set these up, so we have 3 different solutions that are all correct, while unique. First, we will consider the composition to be expressed as h of g of x, just to make sure that our terms don't get confused. We could think of this as 3 plus the square root of g of x. Thus, we have that h of x is 3 plus the square root of x, and g of x is 5 minus x squared. we'll place a box around this as to signify that it is a correct solution while not being the only one. We could also think of h of g of x as 3 plus g of x. In this particular case, we're saying that h of x is 3 plus x, and g of x is the square root of 5 minus x squared. This is a correct solution. While distinct from the first, we will put a box around this. Finally, we have h of g of x as 3 plus the square root of 5 minus x squared. If we allow this to be our function h of x, 3 plus the square root of 5 minus x squared, we could call g of x just x, and we will place a box around that. Our third solution is called the trivial solution, and while it is always the case, it will not be a viable homework or test solution for this course. It's important that we understand that the trivial solution is in fact trivial and doesn't necessarily demonstrate competence outside of simple rote memorization. Analyzing function compositions. Given that h of x is equal to the square root of 2 minus x and k of x is equal to 3 over x plus 4, determine the domain of k of h of x. We have a number line going from -5 to 5, arrows on both sides to signify that this number line extends indefinitely in both directions, and we have a red line to signify our implied domain, also extending the entirety of the number line going in both directions. As with our assumed domain, we assume that the domain is all real numbers until we see the algebraic restrictions on those domain. Our procedure. First, we will compute the composition. So first we will compute k of h of x. Thus, everywhere we see an x in our function k, we will put the equation square root of 2 minus x in its stead. So what we are computing is k of the square root of 2 minus x. Thus, we have the function 3 divided by the square root of 2 minus x plus 4. Now that we have the composition, we will find its domain. The second step of our procedure is to remove divisions by 0 from the implied domain. In order to do that, we will consider the denominator, and in particular, only the portion under the square root, as the square root does not change the possibility of the 0 in the division. So we are really setting out to solve the equation 2 minus x equals 0 and remove that solution from our implied domain. We will add x to both sides, and we have that x equals 2 is our solution. Thus, on our red line, we now remove the point 2 and place an open circle in its stead to signify that 2 can no longer be considered as a point in the domain of the function k of h of x. Next, we will remove negatives under even-indexed radicals from the implied domain. Since we have a square root, its implied index is 2. Thus, we cannot have a negative number under that radical. So we do need to solve the inequality. 2 minus x is less than 0. This will tell us where we would have negatives under the radical with even index. We will add x to both sides, and we have that when x is greater than 2, the radicand will be negative, which means we will no longer have a real number as our output value for the function. Thus, we delete the right-hand side of the implied domain after the open circle at x equals 2. What we are left with now is our actual domain is represented with an open circle at the point x equals 2, and our red line, which is our resulting domain, is a ray extending indefinitely to the left. Thus, our solution is parenthesis, negative infinity, comma, 2, parenthesis. We use the parentheses to signify that we cannot include the endpoints of this domain. We can't include the endpoint negative infinity because we cannot truly arrive at it. Similarly, we cannot include 2 because we have removed that point from the domain.